Hello, in this video we are going to solve the Atwood machine with mass changing. So this is going to be a cone with sand and it's releasing sand. We are going to make M2 bigger than M1 and we want to find the acceleration of the object or the velocity of the object and the position of the object. We are going to see that the velocity is easier to find. The velocity of is the easiest one to find first. Before doing this, before solving the problem or doing the experiment, we put the cone with the sand and we record the force, which is the mass versus time, and we got this initial mass and then linearly reduces, and then this is the MF is the mass of the empty cone. We are going to focus on this region over here because when we do the experiment it takes a fraction of a second because M2 is bigger than M1, so it's accelerating up, but it's losing mass at the same time. So acceleration is going to be even higher. And we are going to be in this region over here, so we can find this function is the one that is convenient for me. Alpha has units of 1/2, and dm1 dt is the initial mass of the cone times alpha, and is negative. And this is constant. And when we did the measurements of how the sand is released from the cone is a linear function, so alpha is the rate, m naught times alpha is how much mass the cone is losing per second. So the acceleration of M1 is supposed to be faster than the Atwood machine case. I like to put the G at the front. So we are supposed to get an acceleration that is a function of time and bigger than this. If this is the case of alpha 0, then the velocity is just, if it's hold, it's not being pushed or anything, this is my function for the velocity, and the position is just going to be a quadratic function of this. Acceleration is constant. This is linear. Position versus time is going to be quadratic. And we are going to see that now these are function of time, and it's supposed to be bigger than these expressions over here. The first thing that we are going to do is to know what is the same over here than in the Atwood machine problem, and the same thing is that the length of the string is constant, and this implies, let's say L is y1 plus y2. If I put my axis over here, and the initial velocity is 0, so if you take the first derivative of this constraint equation, you get b1 plus b2. So in the same way that you get that acceleration 1 is positive and acceleration 2 is negative, also velocity 1 is going to be positive and velocity 2 is going to be negative. And because the string does not stretch, we got these equations. These are the ones we are going to use in this problem. Now we go to the Newton's second law. The sum of all forces equals mass times acceleration cannot be used. You have to use momentum over time. Why? Because the momentum is changing, because the mass is changing, and the velocity is changing. And remember that m1 is a function of time. Empirically, I know this is true. And now we are going to put the equation for object 1. So you got gravity down. Tension, we are not including moment of inertia. No moment of inertia. So it's going to be 1 tension per string. And this is the equation for object 2. And here is the interesting part, because here we got m1 times b1, but b1 is b. So we got dm1 dt times b plus m1 times dv dt. And this is the one that is mass times acceleration. So if the mass is not changing, you don't have this term over here. Now for the other object, the m2 is not changing. It's a negative over here. So you got 0 times negative v minus m2 dv dt. The negative is because the velocity is in the opposite direction. This is the term that is 0 in that case. So the equation simplifies to this. Let me rewrite the equations, equation 1 and 2. So I rewrote the equations over here, and the derivative of the mass 1 with respect to d is negative m naught alpha. That's this term over here. And now I'm going to subtract the equations, or I'm going to multiply the bottom one by negative 1. So this is positive, this is negative, and this is positive. Now I'm going to add them up. I like to put the positive term first. The tensions cancel. And here I will take I got a mistake over here. So over here is b, and I put dv dt, so this is b. Is derivative of the first one times the second, so this is just b. So I got this new term that does not exist if you don't consider, and then you add the two masses as a common factor. And now I'm going to divide by m2. I'm going to divide by m2. So I get over here, let me get g common factor. This term I'm going to put it to the right hand side. So this is the acceleration of the object, and as you see, if alpha is 0, I get the Atwood machine case. That is the difference of the mass divided by the product of the mass. Now we have this term over here. So this is a differential equation on the velocity. So we could now divide everything by M2. Going to divide everything by M2. I will call and remember that M1 divided by M2 is M0 divided by M2 minus alpha t, and if I distribute this, I get M0 minus alpha t. If I got M1 over M2, I need to put this over here. So I'm going to pass the video and substitute all that. So this is what I get. Remember, this is plus and negative. So this negative made this one negative and this positive, and this one is exactly like this over here, positive and then negative. So now for convenience, I will now divide everything by, I will divide everything by M2 over M0. I don't like this term over here, so I'm going to multiply everything by the whole equation by M2 over M0. So this cancel out, but it's the whole equation times that, and it's taking form. And now I will call this mu plus this term over here, and mu minus this term over here. And this is bigger than 1, than 0. Both are positive because M2 is bigger than M0 by choice. And now I'm going to divide by this parenthesis. So the dVt stays in one side. Then I have to put minus this term going to the other side divided by this parenthesis. Times b equals this function that is mu minus plus alpha t divided by this one that is mu plus minus alpha t. Remember, I just make this a variable. The other way. So this is going to be called p of x of t. It's going to be this function here. And f of x is going to be what is on the right hand side. You're going to see why in a second. So this equation is written like this. This is very important to have it like this, because this is how it is in the textbook. This is my textbook for differential equation and variational calculus. I bought 5 pesos when 25 pesos was $1, so this cost me 20 cents. This cost me 20 cents, and I cannot find a problem that I cannot find the solution in this book. And this one is right here. In the textbook it's always y and x, So y is v, the velocity, and x is the time. This is my function of time, and I just write it exactly like it is. And how you solve this equation? It's not that hard. First, you solve the homogeneous equation. You make the right hand side 0, and you solve it. You integrate. It's very easy because dy is log, and the integral of px dx is what you need to do, plus a constant. So this is the homogeneous solution. And then you make this constant from the homogeneous solution a function, and then find the derivative with respect to x, and you get this expression substituted back in the original equation, and you get an equation for c, that is this thing over here, and then you substitute c over here on the previous equation, and you get the solution like this. So I'm going to just write this solution, but remember that x is t and y is v. So I get v equals, again I just put the solution over here. They call it c1, I just call it c, and this is a function that has the constant, and we are going to see that the constant is going to be 0 if the initial velocity is 0, and we are left with this term. So as you can see, don't need the book anymore. We need to find this integral, I will put it with the minus, and this negative and this negative cancel out, and I get to integrate alpha dt, and now when I integrate this can be written with a negative here again back. This is a constant minus alpha t. I got the alpha over here, just need the negative. The differential of this is 0, the differential of this is alpha dt, and negative is plus, and then I got mu plus minus alpha t, and this is the log function of mu plus minus alpha t. So and I'm going to put this negative over here. That means that the integral is, this is t, no x, is log of 1 over mu plus minus alpha d. And all this is dimensionless. It's very important to have this dimensionless. So I now have these parts over here. So I'm going to put that into the equation now. So, because I got exponent of that, the exponent and the log cancel out, and I got only this. That's why I put it like a parenthesis here. Then plus the same thing over here, but this one doesn't have the constant c. That's why it's very important to have everything dimensionless. Alpha is units of 1 over time, cancel the units of time, so it's very convenient to have everything dimensionless. And remember that my f of t is this. I'm going to substitute it now. And this one doesn't have the negative, so I need to put this like without the negative. Is going to be like this. And if I take log of that, look what happens over here. This cancel, and I just need to integrate a polynomial that is easy. So this is my function of time. Very interesting that you get a ratio. So now, because my initial velocity by choice is 0, all this is 0, this is 0, so C is 0. So this is my equation for the velocity. So I was expecting a exponential function, but I get a rational function. And this is the more compact of the three. You are going to say, oh, if you take the derivative of this to get acceleration, but this is going to be this bottom, the denominator has to be square, and then you get the derivative of the first one, that is mu minus plus alpha t times the second, mu plus minus alpha t. And then the other term, I'm not going to do it, that is the first one times the derivative of the second. So this is going to, but this is going to be a polynomial of second degree on the top and second degree of the bottom. So if you have a polynomial that is second and second, it's kind of a linear, it's not a linear function, but it has that behavior. And if you go over here to find y versus time, you need to integrate the velocity to get the position, and it's going to be even worse. Doable, but even worse. So we are going to stick with the velocity, and if we do the experiment, we are going to collect data of velocity versus time instead of acceleration versus time. That is usually very noisy to have the acceleration versus time, and position versus time is what you actually measure with the motion detector and the devices. So, but probably we are going to get this, and we get velocity versus time by using a pulley that tells how the pulley is moving. So we could get this function from the motion of the pulley over here and compare this with experimental data. Now we are going to take the limit. If alpha is 0, b time is mu minus mu plus times t, and if you remember, this is m0. Let me see how I define it. Yeah, m2 over m0 plus minus 1, m2 over m0 plus 1. This can be written like this: the sum of the masses times, I forgot g somewhere. Let me see, I think I forgot the value of g. You see this value of g over here. Here and here. So here I forgot to put g, and here I forgot to put g, g, and g. And g. So this is the equation. Forgot to put the constant on g on that side of the equation, that is here, and then 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 here, and here. Okay, so this is the solution. So how to test this is right. So if you could see, let's say I don't change the masses for simplicity, and I repeat the measurements as many times as I want. Then my constants are alpha and g. But alpha, I know it when I put the cone with the force sensor. So we know what alpha is, we know what g is. So what I would do in this graph is to plot, get the experimental measurements of the velocity. It's supposed to be something quasi-linear, because this is t squared over t, and I will plot the data point, and then I will fit my function and see if this equation matched the data. In that way I will validate that this is correct. Another way to do it is you got the data, and this is n, the number of measurements, and I will do the function minus the value. The experimental are the dots, and then I evaluate my velocity at those times, and I'm supposed to get this. And this is my number of measurements. And then I will histogram this. And then I know how precise this function fits the data. Again, there is no moment of inertia over here in the pool.